Hello, I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 22nd instalment in CompBiomed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. We've got quite a special talk for you today, as we're joined by three speakers from NVIDIA: Paul Graham, a Senior Solutions Architect, Robert Dietrich, a Senior Systems Software Engineer, and finally Felix Schmidt, a Senior Software Engineer. The overarching theme of the three talks today is the efficient use of GPUs for high-performance computing, and we will see some of the technologies, tools, and techniques developed within NVIDIA that are aiding this goal, including some live demonstrations. First up is Paul Graham, who, as I mentioned, is a Senior Solutions Architect. It is his responsibility to support customers and partners in delivering accelerated solutions across a number of scientific communities, such as research, high-performance computing, and artificial intelligence. And before joining NVIDIA, he spent 20 years at the Edinburgh Parallel Computing Centre. Paul's talk will explore some of the technologies out there for reducing bottlenecks within and across nodes, including the use of some standard language features for GPU programming in C++ and Fortran, for example, directives-based approaches such as OpenMP and unified memory, with an overview of GPUDirect for optimizing the communications pipelines. Now, before we begin, I'd like to briefly remind you that the session is being recorded and will be available on the CompBiomed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and maybe even share these e-seminars with your friends and colleagues. There will be an opportunity for questions at the very end of the session today, rather than in between the talks. So please save your questions until after all of the presentations have finished. Once that time comes, you can post your questions in the questions tab and I will read them out for you to Paul, Robert and Felix to keep the session running smoothly. Now that's everything from me. I very much hope that you enjoyed today's talks, and without further ado, I'll hand over to you, Paul.
Thank you very much, Tim. Thank you for the introduction, and thank you for giving us the opportunity to speak today. It's our absolute pleasure to do so. As Tim mentioned, I'm a solutions architect, and my job is basically to advise people on making use of their GPUs in the best possible way. You know, you've bought a GPU, you want to make sure you're making use of it efficiently, making sure you're getting the best performance out of it, and utilizing your resources very, very efficiently. So without further ado, let's just crack on. We've got a lot of material to get through today. The session is going to be split into two components. Firstly, I'll look at different ways of programming for GPUs and some of the tools and technologies which will help you sort of minimize bottlenecks both within and across nodes. And then we'll look at things like GPUDirect as well, which is ways you can communicate between GPUs both within and across nodes, and now indeed with storage directly with the GPU. So again, it's removing the bottleneck of the CPU. And I'll touch a little bit on some of the visualization tools at the end as well. After I've spoken, we will go through a couple of live demos of some of the profiling tools. And I think it's really important to stress this. You know, if you're working on a GPU code yourself, you need to really understand where the bottlenecks are happening before you start spending time trying to optimize. And to help you with that, we have two tools we're going to demonstrate today. The Nsight Systems tool, which is looking at profiling your application at the systems level. So that's, you know, within a node or across nodes. And then we have the Nsight Compute tool, which allows you to have a real deep dive into what the GPU is doing under the bonnet. And my colleagues will cover those in the later sections with a live demo. So I think that'll be really good. Okay, so let's just have a bit of background. So what are we seeing with GPUs at the moment? Well, they're being used everywhere. And there's a really huge ecosystem of applications and codes which make use of GPUs. But this wasn't always the case. Of course, GPUs were originally designed for putting pixels on a screen, and they were designed to do this many times a second, so thousands of pixels many times a second. And because of that, they're designed as a very parallel architecture from the bottom up. You can imagine the calculations you need to perform on each of those pixels are very similar across all of them. And so the hardware itself was designed from the bottom up to be parallel. And this contrasts quite starkly with the CPU, which of course was designed originally for running things like operating systems and essentially serial tasks. And the challenges we've seen in the last 15 years or so in terms of hardware is that the single-threaded performance of individual cores has kind of been leveling off. It used to be the case that we could rely on just buying a new CPU, new piece of hardware every couple of years, and we'd see our thread performance pretty much double. But that's been tailing off due to various considerations, such as heat management on the device, how many actual transistors we can fit on a single device, and so on. And so to compensate for this, we've seen CPUs moving to a more multi-core architecture, but indeed that requires your algorithms to be written in parallel anyway. And if you're going to start using parallel algorithms, then you probably want to consider using an architecture which has been designed for parallelism from the bottom up, and of course that's the GPU. And we can see from this example here that the GPUs have been used in a very, very broad field. Of course, we'll all be familiar with GPUs being used for simulation, astronomy, astrophysics, molecular dynamics, and so on. But of course, another driver behind the ubiquitous nature of GPUs in modern systems is the applications of AI. And the calculations which are at the heart of deep learning are very, very good fit with the GPU hardware. And again, that's one of the driving forces that for the reasons that we see GPUs in many modern large systems. And of course, the way the GPUs work, they still work with the CPU. The basic idea behind them is you have your code. There'll be a certain part of your code which is very computationally intensive, and that takes up 99% of the runtime of your code. And that's the part of code that you'd like to optimize and ideally parallelize and offload it to your accelerating device, in this case a GPU. And it's conceptually, it's quite a simple programming model. There'll be some parts of the code which remain on the CPU, but the really computationally intense parts of the code you want to offload to your GPU. And of course, as we move to the exascale era, we want to offload to tens, hundreds, even thousands of GPUs to do this in order to try and continue on this line of improving our performance year on year. I've got one slide, well, two slides about the hardware. Today's focus is not on the hardware, but there's a couple of features in the latest generation of hardware which I think are important to mention, just for those of you who aren't familiar with them. Firstly is the tensor cores. So tensor cores are aimed at doing matrix, multiply, and accumulate operations, and I've got a whole slide dedicated to those coming up. But of course, there are many calculations which require matrix multiply operations, and of course, many of those in the world of deep learning. And that's kind of where the drive for the tensor cores have come from. We also have a thing called multi-instance GPU. The modern GPUs are becoming more and more powerful, and there's lots of applications which actually can't exploit the full power of a whole GPU itself. Or you have a usage environment where perhaps you don't need the full GPU just to yourself. Perhaps if you're working in a research environment, you want to share your GPU resources amongst your team, for example, when you're developing your code. So we've introduced a thing called multi-instance GPU as well. And this allows you to slice up your GPU in a hardware sense into smaller GPUs. Still, each of them very, very powerful, still with a large amount of memory available to them, but it allows several users to share the same GPU at the same time, and their work won't interfere with each other's work. So I think that's something of real interest to researchers, especially. You can during the day you can share your system amongst many researchers, and then at night perhaps run your simulation using all the GPUs together. And we also have the NVLink and NVSwitch technology. Again, I'll speak a little bit more about that later, but essentially that's aimed at speeding up the communications on a node between the GPUs. So I mentioned tensor cores, and this is dedicated hardware on the GPU for doing matrix multiply and accumulate operations. They were introduced in the Volta generation. Oh, sorry, I've clicked on, excuse me. In the Volta generation of cards, and on that generation, they performed these matrix multiply and accumulate calculations at a mixed precision. So they would take in single precision data, they would do the multiplication FP16 half precision, and then they would output the accumulated answer in single precision again. Then in the Turing generation of tensor cores, we introduced the support for int8 and int4, and a lot of this was driven, as I mentioned earlier, by the use of the matrix multiply operations in deep learning. And in deep learning, quite often you can manage to do these calculations at lower precisions and not have a detrimental impact on the performance quality of the models that you're training. But now with the Ampere generation, we've actually introduced full double precision support in the tensor cores. And again, this means if you are using matrix multiply operations within your code, then it's a really good idea to offload onto the tensor cores to take advantage of that. And in addition, we've introduced a couple of extra data types as well, again, aimed at the world of deep learning, but that's not to say that there aren't algorithms in the world of high performance computing which can make use of the mixed precision approaches. So if you're coming to the GPUs for the first time, probably your first experience of using one will be via an application or a framework which is already written to take advantage of the GPU. So in the world of deep learning, we have the major frameworks such as TensorFlow and PyTorch, for example. They all have GPU accelerated versions with multi-GPU and multi-node support built into them. So that's a great way to get started if you're doing that sort of thing. All the top 15 of the world's most used high-performance computing applications have GPU accelerated versions. So again, you're taking advantage of the fact that a lot of effort has gone into making those codes run as quickly as possible on the platforms, so you don't have to worry about that. But of course, there may be an application which isn't yet ported onto the GPU, or you have your own application which you're working on, and in which case you need to think about how to program for your GPUs. And the first approach many people would take is just to use a library. If we think about all the typical libraries you see in the world of CPU program, Fourier transform libraries, linear algebra libraries. Of course, there are GPU accelerated versions of those. And that's a really good way, again, to take advantage of the fact that a lot of work has gone into making these libraries perform as well as possible and saving you time and effort. After that, you may want to think about taking more control over what's happening in your code. Perhaps a particular library doesn't support exactly what you're trying to do. So you may want to think about starting to write your own GPU code. And a really good way to do this is to take the directives-based approach. And here I'm thinking about things like OpenACC, which was designed from the bottom up to work with GPUs. And then latterly, of course, OpenMP, which over the last few years has seen support coming in for offloading onto GPUs. And then, of course, if you want to have maximum flexibility, maximum control over what's happening, then you probably want to use a dedicated language for the particular device you're working on. In our case, that would be CUDA, for example, which, of course, exposes all the features of that underlying hardware. Going back to the maths libraries, again, if you can make use of them, I think this is a really good way to go because an awful lot of effort has been put into making these perform as well as possible. And the direction we're going with our library support is we're trying to scale them up. We're trying to introduce both multi-GPU and multi-node support in those libraries. We're also trying to make sure that all the libraries support all the features of the hardware. For example, if you use our QBLAST library, it will take advantage of the tensor cores for you if at all possible. And that's something which we think is really important. You can, of course, program for the tensor cores directly yourself, but that requires a lot of developer effort. So in terms of what we would call developer velocity, how quickly you can get your code up and running well, I think the library is a great approach and they can exploit the tensor cores on your behalf. And in fact, this slide shows you some of the support that we have for making use of the tensor cores in the maths libraries today. So you can see the linear algebra libraries, of course, the QTensor library, which is looking at essentially matrices at higher dimensions, QSolver, which is our linear solver library, and so on. And basically, you have full support there for accessing the tensor cores. And indeed, if you want to program for the tensor cores directly, I'll just mention here that we have our Cutlass library, which is a suite of APIs for programming directly for the tensor core. So if there's a particular operation that you think you can perhaps get even better performance out because you write a dedicated bit of code for that particular operation, then Cutlass is the way to go for the tensor cores. I mentioned the fact that one of the directions we're going in is to try and bring multi-node support as well as multi-GPU support into the library. And here's a good example of our QSolver library, which is looking at solving linear equations. And this is an experiment we did on Summit, which is one of the, I think it's currently the second largest supercomputer on the top 500 list at the moment. And here we have what was previously the state-of-art implementation of a multi-node solver, that's the gray line. And now with our new QSolver MP library, you can just plug that in and you can see there's a real leap in performance across the two comparisons there. And of course, it scales very well up to 1,000. That example, up to 1,024 GPUs. So this is a compelling argument for why you should consider looking at the libraries and seeing if you can make use of those. Similarly, we have the QFFT-MP, which is a fast Fourier transform library, again, running very, very well at scale. And we can, again, this was run on Summit, the gray being the original sort of best performance that people had seen, the green now being the performance you can see just using our library. So again, if you have a problem which can scale to that size and can make use of FFTs, that's a really good approach to take. And this is the direction we're trying to go with all of our libraries. Once you've had a look at libraries and perhaps the libraries don't do exactly what you want to do, as I mentioned, you may want to think about programming. And if we look historically at the way programming for the GPU is developed, it's kind of going from right to left on this particular slide. And before the right-hand side, so before CUDA came in, developers tried to program their scientific code using GPUs by just using the sort of language of graphics. So they would use shaders and various other graphics APIs. But that didn't really match well to the algorithms that they were trying to do in high performance computing, for example. So it was quite awkward and quite niche. And so very few people were actually able to leverage the full power of the GPUs back then. But then CUDA came onto the scene, and this was a great leap in sort of accessibility to GPUs for just normal developers. It meant they could write code in a way which looked familiar to them. They could write their algorithms in a way which looked very similar to the way they'd write for a CPU system. But now, not long after that, people will say, well, it's still quite complicated to program in CUDA, and we need something perhaps more portable. And that's when the directives-based approaches come in. So things like OpenACC and, of course, OpenMP. And what these allow you to do is make sure that your code is portable between both CPUs and GPUs. It also allows you a very good incremental approach to parallelism. If the system doesn't support OpenMP or OpenACC, the directives are just ignored, and the code will still run correctly, for example. And also it means you didn't really have to worry too much about changing your algorithms. Changing your algorithms was perhaps considered as a performance optimization you could do afterwards, but in terms of actually just getting things up and running in parallel on both the CPU and the GPU, the directives-based approach is a really good one. But now I think the direction of travel we're seeing is trying to take advantage of the standard languages themselves. For example, in C++ and in Fortran, for a few years now, there's been support for expressing parallelism just using the standard languages. No extensions, no additional libraries needed. It's just the standard languages. And we think that's a really good direction of travel, because it means you're ensuring that your code remains portable. It's just using the standard languages, no extra features. But also means that as a programmer, you don't perhaps have to think too much about what's going on underneath the bonnet. You can just express your algorithms as you would normally in the languages that you're familiar with. And to help support this, we in our compilers now provide a way of taking this code written in standard languages, and we can compile it for both either the CPU or the GPU, and it will run in parallel and actually get decent performance out of it. So we can stop thinking about porting to an accelerated system. You can just think about optimizing on whichever system you're running on. So if I was coming to programming for GPU nowadays, I'd probably suggest looking at the slide and taking this approach left to right here. So start off with the standard languages, program in the way that you're familiar with. Then if you want a little bit more control over what's happening, perhaps for things like the data movement between the CPU and the GPU, you could introduce the directives-based approaches. And then if you want to get absolutely maximum performance, once you've done your profiling, and we'll talk a little bit about that in the later talks, you've understood from your profiling that perhaps you're not seeing the best performance you could expect, then you'd move to probably a device-specific language such as CUDA in order to squeeze the last few percentage performance points out of it. Excuse me. So we have our compiler suite, the HPC SDK. This is absolutely free, and it's with these compilers. So it's got C compilers and Fortran compilers, which support this standard language approach. And I have to stress on both the CPU and the GPU, so you can write parallel code for the CPU using this approach as well. With the HPC SDK, of course, you get all the maths libraries and the various communications libraries as well, and the profilers, which we will be talking about later. So with our compilers, what you can actually do is mix and match the different languages approaches. So you can start off with standard languages, then you can just add directives to that code. The compilers will support that, and you can even include CUDA in there as well. And the compilers can support all those different paradigms working together. And as I stressed, it works very well for the CPU, and we provide multi-platform support in terms of the CPU side of things. So of course, x86, OpenPower from IBM, and now ARM support as well. So let's look at what you can expect to see with C++. So this is looking at, I believe, the Lulesh hydrodynamics code. And on the left, I realize it's a very busy slide, but it's kind of, the point of it is to show you that the code on the left is quite complex. And that's a code which has been parallelized using OpenMP. The code on the right does exactly the same operations, but it uses modern C++. To do that, and also uses the standard C++ way of expressing parallelism. And so what we have there on the right is something that's very much more composable, it's very much more elegant and compact, but will actually run, if you compile it without compilers, in parallel on both the CPU and the GPU. So let's look at the kind of performance we can get from that. So on this slide, blue is representing the GNU compiler version. So our baseline is the OpenMP version, which you saw on the previous slide, running on 64 cores of a EPYC CPU. So that's the one on the left, with the one next to it. Then there's the our compiled version of the OpenMP one, which gets slightly better performance, nothing too great to write about. But then if we look at the performance of the standard C++ one, we're seeing a jump in performance already just from moving that code from this rather complicated version to the simpler version. Perhaps that's exposing something to the compilers that they couldn't previously see, which has allowed them to make further optimization. So again, even just moving to that standard C++ approach has cleaned the code up a bit, so we see performance improvements just on the CPU alone. But of course, the powerful thing is here that with exactly the same source code, we just change a compiler flag, we can compile a version of that code for the A100, and we see significant performance improvements from doing that. And I think that's a really interesting approach. Now, of course, this is all relatively new. Some of the features in the language won't be along until the next release of C++, and then similarly for Fortran. So it's not going to solve everyone's problems all of the time, but I think it's a really good approach, and the support for this approach is only going to improve as the years go on. So that is one of the reasons we're really driving behind that. And of course, Fortran is really important. I'm historically a Fortran programmer, and of course there's many codes out there written in Fortran, and the reason those codes still persist is because Fortran is a nice way of writing scientific code. And within Fortran itself, there's also support for expressing parallelism, and the main one which we support now in our compilers is a thing called do concurrence, and this basically says to the compiler, I'd like this to run in parallel either on the CPU or the GPU. So again, let's look at an example. So on the left there, we've got a matrix multiplication code, sort of handwritten code. You could spend a lifetime of research trying to get the absolute best performance out of the particular machine you're running on, using unrolling, vectorizations, and so on. And you still probably won't get anywhere near to the best performance that a library could do. And so what we've done with Fortran is there's an intrinsic called mapmul for doing matrix multiplication. And in the background, we actually use one of our CUDA libraries, QTensor in this case, is invoked, and that actually runs the mapmul multiplication. So you can see from the graph on the right there what sort of performance impact you can expect from that. So looking at the V100, the sort of naive code on the left there with no real optimizations done doesn't get very good performance at all. Then you look at the Fortran mapmul version in the middle there on the V100. And for those of you familiar with the V100 platform, will note that that's pretty much hitting the peak performance we could expect to get from the V100, and that's because it's using the QTensor library in the background. But of course, the code itself is absolutely portable and parallel. There's nothing in there intrinsic to CUDA. And then on the A100, again, if you're familiar with the A100 platform, you'll notice that performance is actually, that performance level is achieved by making use of the tensor cores. So not only are we running in parallel on a GPU just by including this mapmul function, we're actually taking advantage of the tensor cores as well, because the library underneath is understanding that it can use the tensor cores on the A100 to do that. And hence we're seeing that huge leap in performance between the V100 and the A100. And this isn't just a one-trick pony. Basically, anything which looks like a matrix multiplication combined with a permutation can all be supported by the Qtensor backend. And this slide just shows you a few of the different examples of matrix operations you can express, which you could then expect to be accelerated on the GPU. So Fortran is very, very much alive and kicking, and I believe well supported within the NVIDIA environment. So we're asked about unified memory quite often, so let's just cover that. For those of you not familiar with it, it's a unified memory, or managed memory as we sometimes refer to it, is a technology that basically allows you to represent what are actually physically separate CPU and GPU memories as a single shared pool of resources. So as a programming nicety, this is a really nice way to approach programming. You don't have to worry about explicitly moving the data between the CPU and the GPU and vice versa. The runtime driver handles all that for you by a page faulting system. So it's a really great way to get started, and you should use this and basically think of being explicit about your data transfers again as a performance optimization. You know, measure your code's performance, see if the data transfers are actually having an impact, in which case you may want to manage them directly yourself, but if not, you can just stick with the unified memory model. So the disadvantages of the managed memory, as programmers, obviously we can understand the full flow of our code perhaps better than the compiler can, and in which case we can perhaps better understand whether data transfers need to take place, whether they can be overlapped with compute and things like that. So obviously as programmers we can do those things, whereas the way the managed memory works is quite reactive. Basically, when it tries to access data on the CPU or the GPU, if that data isn't already on that device, it will move it across. So if we can anticipate those movements, we might be able to speed things up. And actually setting up the managed memory allocation takes a bit longer than it does in managed memory. But again, that's not necessarily a huge consideration. You tend to do that once at the start of the program, and then it just persists for the whole lifetime of the program. In terms of advantages, as I mentioned, as a programming nicety, it's a really great start. You don't have to worry about doing the explicit data transfers yourself. It leads you to focus on the parallelism and, as I mentioned, think about data movement as an optimization. And another really powerful thing, which sometimes doesn't get mentioned, is the fact that this helps support oversubscription. So basically what I mean by that is when we have a data set which is actually larger than the GPU memory we have available to us. And you'll see that the word oversubscription is highlighted in green. That's actually a live link. We will share a PDF of these slides after the event so you can take a look for yourself. But that's a link to a developer blog about oversubscription, and where using managed memory is actually a really good approach to handle data sets which are larger than GPU memory, and what sort of performance you can expect to see by doing that. And essentially the managed memory just swaps out the data for you. You don't have to explicitly do it. So that's really quite a nice feature of it. In terms of using managed memory with the different programming models, and if you use the compiler flag -ta equals Tesla managed, that automatically switches on managed memory for you. So all the data transfers in your OpenACC code will be handled by the unified memory. Using the standard parallelization approaches, such as the ones in C++, again, the managed memory is implicitly used there. All the data movement is handled using the managed memory. And in OpenMP at the moment, it doesn't support the managed memory model, but that's not to say it isn't on our roadmap to do something about that. But at the moment, you still need to use the target map directive within OpenMP to move the data around. So moving on to thinking about programming at scale, and not just program at scale, but some of the hardware features that you need at scale. So first of all, if we think about the communications between the GPU and the CPU, the latest generation of GPU cards supports PCI Express 4, which is pretty much, I think, double the bandwidth of the previous generation, so that improves that bottleneck. But when we think about communicating between GPUs within a node, we can do better than the PCI Express bus, and that's by using a thing called NVLink. And this allows the GPUs to communicate directly without having to go via the CPU. The bandwidth of the NVLink is much higher than the PCI Express bus as well, which means that if we do have inter-GPU communications, that's a great hardware feature to make use of in order to speed up communications significantly. On some of our larger boards, so the ones with 8 GPUs on them, we have a thing called NV switch as well. Basically, on those, all the NV links go directly into the switch, and the switch provides fantastic all-to-all communications between all the GPUs within a node. I mentioned a thing there called MPS. That's multi-process service. If you're running an MPI code, for example, this can be really useful to try and help balance out your workload, and also try fully exploit all the power of the GPU. So this allows you to have multiple MPI processes per GPU. So it allows you to better balance perhaps your CPU cores with your GPU, which you have in your system, but also it basically allows you to effectively have several codes running at the same time on the GPU, which can increase the throughput. And there's a live link there again to the blog based on the GROMACS code, which my colleague Alan Gray works on, where he used MPS to significantly increase the throughput of GROMACS. So that's an interesting read if you're interested in that sort of thing. So we also have GPUDirect. So GPUDirect has been around for a few years now in a few different invocations. First of all, there was peer-to-peer, so this is allowing GPUs to directly communicate to the memory space of other GPUs on the same node. Then there's RDMA, Remote Direct Memory Access, which again, same principle, but across nodes, so the GPUs can directly access the memory between nodes. Again, cutting out the bottleneck of having to go via the CPU. And then just last year, I think it was, or at the end of the year before, we introduced GPUDirect storage. And again, this allows you to directly put data from the file system into the GPU memory, avoiding having to go via the CPU. And all these things are aimed at the idea of reducing bottlenecks across the system. And on the road to exascale, we have to think about these things. Any communication bottleneck can impact your code, and the larger scale you're running at, the more impact it's going to have. So I think these are very interesting features. In terms of networking side of things, of course, NVIDIA acquired Mellanox. I think it was, it seems like maybe 2 years ago now. I think it was the start of lockdown. And of course, along with that, you get the excellent interconnect between systems, but also we've introduced the data processing unit. So the Bluefield line of data processing units. The idea there is that we can perform operations on the data as it's moving through the system, for example. Also, we can offload some of the work that the CPU has to do onto the GPU in terms of things like virtualization, for example. We can have software-defined storage as well via the GPU. So again, it's another tool for releasing up the CPU and the GPU to do what they're good at, and it takes care of the other things. I wanted to say something about NVSHMM. So hopefully those of you who work with GPUs and work with MPI understand that there's CUDA-aware MPI. So CUDA-aware MPI allows you to directly invoke your MPI calls with the memory on the GPU, rather than having to first of all copy to the CPU and then invoke your MPI call. So CUDA-aware MPI again is a very useful tool. What NVSHMM is a GPU-optimized implementation of the OpenSHMM standard. So this is a PGAS approach, so it's a partitioned global address space implementation. And this can have advantages over MPI, especially for one-sided communications. So it provides this sort of ease of use of a shared memory model, but with the performance of a distributed memory programming model like MPI. And again, it also brings improvements in terms of developer velocity. You can have much fewer lines of code quite often than you can with the MPI equivalent, and thus, reduce your time producing science, but also see speed ups in terms of performance. And there's the one particular code we've seen great performance in is the quantum chromodynamics set of libraries, CUDA with a Q. That's moved from an MPI to an NVSHMM approach and seen really good performance improvements. So that's something else to make you aware of. Okay, I just want to say a little bit about visualization. Just quickly touch on things. So, of course, graphics cards are good at putting pretty pictures on the screen. Hopefully we all understand that. And with our RTX cards, we now have real-time ray tracing support. And what that can do is bring almost photorealistic qualities to the images that we can create, which from a scientist point of view may give you better insight as to what's going on, but it can do that in real time as well. So you can be looking at live data and you can apply the RTX to that and get very, very good images out of it and hopefully make better understanding of your data. And in order to help scientists make use of the ray tracing, we've incorporated the RTX abilities into the scientific visualization tool ParaView. So you can switch easily between a ray tracing approach or a rasterization approach. It works well on a workstation or in client server mode. In addition to the RTX side of things, we have Index, which is a volume renderer. Again, that's available within ParaView, and this allows you to render large structured and unstructured data sets in a GPU accelerated manner. So again, I think what this really helps promote is, better understanding of your data, but also you can interact with your data much more quickly by using the GPU approach. In terms of point cloud rendering, this is now very scalable. Again, in using the NVIDIA Index tool, we use an approach called a radial basis function, which allows us to basically do large scattered data point set interpolation. And here's a couple of images which have been created using that approach. And again, it makes use of the ray tracing cores on the RTX suite of cards. Now I've got a little video here. Now, unfortunately, we tried this earlier and the video doesn't look very good over the internet for you guys. So there's a link at the bottom there, which I believe will be shared in the chat. So you can, by all means, go and look at this video yourself. Take a look in much higher resolution than I'm going to show you here. But what this is actually visualizing a very complicated data set for a tornado. So ordinarily, this would take hours to visualize and render because of the size of the data set and the complexity of what you're trying to do. However, this has been visualized using the Index tool, which we spoke about. It's also making use of GPUDirect storage in order to access the data set and make sure that we can get that data in and perform the rendering on that data as quickly as possible. So the sequence we're looking at here shows 6,000 simulation steps of a tornado simulation. It is also making use of a thing called NanoVDB, which is a sparse volume data structure, which helps reduce the dataset sizes and the memory footprint of that. And as I mentioned, this uses GPUDirect storage. We're achieving 47 gigabytes a second via that, which means we can review our results at more than 10 frames per second. And what this increased bandwidth also allows researchers to do is actually navigate interactively with the visualization. So they can zoom in, they can sweep through the simulation, and also we can add the photorealistic qualities as well. And also we can do this in a thing called Omniverse. So I just want to touch on Omniverse here because I think it's an interesting tool. And what Omniverse was designed for was basically to allow collaboration on digital assets for creators. That's where it came from. But of course, we're now seeing that being used in a scientific sense, where basically people can create digital assets, be it digital twins of real things. They can add physics to that, they can add AI to that, and they can then collaborate with their colleagues across the world and all interact with that asset at the same time. So I think Omniverse is going to be a really interesting tool going forward, especially in the world of visualization, but also the idea of digital twins as well. Okay, one final word. If the only thing you take away from this is this slide, then I'll be happy. So what this slide is showing you is the performance of a basket of high performance computing applications. So there's a mixture in there. There's things like GROMACS, there's NAMD, there's PyTorch representing the sort of deep learning side of things, there's Quantum Espresso and so on. And what you'll see on this graph is that when a new card comes in, we see a leap in performance, as you'd expect. So you go from the P100 to the V100, the performance doubles. But during the lifetime of the V100, we see the performance of this basket of applications improve. And that's through all the work that goes on the applications themselves, on the libraries which the applications make use of, and the programmers, both ourselves and the community who works on these, making use of the new features introduced with a new card. And again, if we go from the V100 to the A100, we see a leap in performance because it's a new generation of hardware. But during the lifetime of the A100, we've already gone up from 9x to 13x compared to the P100, and we fully expect that to continue in a similar manner. So if you keep your applications, your libraries, and the frameworks you're using up to date, you can get this performance improvement for free during the lifetime of your GPUs. So that's something I just really like to stress. Okay, I've got several slides on resources. I'm not going to go through them all. They're there more for reference for you to look at after today's talk. But just to say that this talk is quite timely. It's our GPU Technology Conference next week, which is absolutely free to register for, and there's a link there. And there's several talks going on which cover pretty much most of what I've talked about today, but in a lot more detail. I've given you a sort of whirlwind view of some of the features you might want to make use of. If you're interested in particular one of those features, then I recommend sitting and having a look at some of the sessions which are going to happen at GTC next week. And just to highlight, there's some of the sessions are called Connect with Experts. Those are not just presentations. You can go along with your own questions there and try and get help on what it is you're trying to do. So again, those are very, very useful to attend in person. And if you do register, you can get access to recordings of the sessions after the event itself. I think that is all I wanted to say. Yeah, there's just some more links for you to read at your leisure. And just to say that that's it from me. So I think now I will be quiet and hand over to Robert.
Fantastic. Thank you very much, Paul. Just a reminder to the audience that we will not be holding Q&A sessions in between talks, but rather that will be saved until the very end. So now the second two talks today are somewhat complementary as we shift towards the identification of bottlenecks, whereas Paul was speaking more of how we overcome them. This is achieved using profiling tools to analyze GPU accelerated applications to target the computational processes that withhold us from achieving optimal performance. And two such tools are Nsight Systems for system-level analysis and Nsight Compute for GPU kernel analysis, both of which will be demoed for you today. Now, the next speaker will be Robert Dietrich, a senior system software engineer at NVIDIA, whose experience in high-performance computing spans a period of 10 years. After graduating from Dresden University of Technology, he worked on the standardization of tool interfaces in OpenACC and OpenMP, and earned his PhD in performance analysis of scalable applications on heterogeneous system architectures. Before joining the NVIDIA Nsight Systems developer team, Robert engaged in research on cluster-level monitoring and analysis. Now I'm going to hand over to Robert for the second of today's talks, in which we will explore the Nsight Systems profiling tool. So over to you, Robert.
Thanks, Tim, for the introduction. So it's also a pleasure for me to talk here. And I'm going to split this talk basically into two parts. So first, I'm going to talk a little bit about facts about Nsight Systems and where it lives in the Nsight tools universe, and also a little bit about NVTX. And in the second part, I'm going to show you in a live demo how a profiling report generated with Nsight Systems looks like and how you can kind of navigate through it. All right, so let's start over. Okay, so the application optimization process, which actually is a cycle, is something you have probably seen quite often in the context of performance analysis talks, so nothing new to you here. So you start your profile with start your cycle with profiling your application, then you investigate the results, take your conclusions, and put them into some potential optimizations. If you are not happy then with the performance, you start over, create another profile, or maybe you just create another profile to verify that the changes worked out as expected. So a very good thing with the Nsight tools is that we do not need an application preparation step. So no compile time instrumentation of resource code is necessary here. You can just, on the command line, you can just prefix our tools or use the GUI for the application invocation. This slide here shows you the Nsight product family. So with Nsight Systems for the system-wide top-down analysis, Nsight Graphics for the graphics applications, and Nsight Compute on the bottom left here for very detailed GPU kernel performance analysis. So assuming a top-down analysis, you would start your application tuning process with Nsight Systems. And the idea is to first analyze and optimize the overall parallel execution, for example, optimize synchronization, data movement, copy compute overlap, etc. And then you would move to an in-depth GPU kernel analysis with Nsight Compute. So for compute applications, you would probably first figure out with Nsight Systems performance relevant kernels. So those are usually the ones with the most runtime impact. And then you would dive into a more detailed kernel analysis with Nsight Compute. After that, you would probably come back and re-inspect the overall workload behavior with Nsight Systems again. So in case of graphics applications, you would use Nsight Graphics instead of Nsight Compute. So however, this talk right now is focusing on Nsight Systems, which is NVIDIA's tool for system-wide application tuning. So what can it do? So it can track your application's behavior, and thus it can give you the means to locate optimization opportunities. The GUI allows the visualization of millions of events in a timeline and provides you with the means to spot gaps of unused CPU and GPU time, and also time where your network interface card is not active. So since NVIDIA is also a network company right now, we also started to support more in terms of networking. So you can also figure out when network interface cards are not active or not utilized much. Another central point of an analysis with Nsight Systems is to support you in balancing the workload of your applications across multiple CPUs and GPUs. So therefore, Nsight Systems collects information on the CPU activity and of course, a whole lot of detailed information on what's happening on the GPU, including GPU context switches, activities on CUDA streams, CUDA kernels, GPU data transfers, memory usage, etc., etc. So with recent versions of the tools, you also get information on the usage of your network interface cards, or in short, we call it NICs. All major platforms are supported, so operating systems, Linux, Windows, Mac OS X, and also CPU architectures such as x86, 64, Power 9, ARM server, and Tegra. So this is just for an overall overview on the general features and support. Let's go over this pretty quickly, since it is a teaser for the demo, which is following in a couple of minutes. So when your profiling run with Nsight Systems finished and you open the report in Nsight Systems GUI, the first thing you see is the timeline view. So it consists of several timeline rows. So we'll see labels on the left here that show you how the application is interacting with the various system resources over time. So the profile shown here is from a deep learning app using TensorFlow. So we have a scenario which obviously focuses on GPU activity and on what might limit the GPU to run at full load. So this is obviously an intention of NVIDIA tools to get most out of your GPU investment, right? Well, Nsight Systems is packed with so many features that we cannot talk about all of them. A few of the features here are highlighted in the screenshot in these green text bubbles. So on the left, you see here the API tracing of CUDA libraries and also of deep learning frameworks. In the top bubbles here, you see for CPU utilization and CPU thread states, thread migration, as well as CPU call stack sampling is also possible. You can also get OS runtime library calls and, of course, GPU activities and also GPU metrics. But we'll have a look at that later on in this presentation here. All right, so before we start looking at a report and its visualization, we take a look on how the profile is generated. If you are on a command line or in a console, you can, in most cases, simply use the basic profiling command, which is called ansys profile. So if you want to know all about the available options here, you can just type ansys profile --help. And after the presentation, you can, if you want, you can look at the video here where the link is below, which explains you how you can run interactive sessions. But for now, let's ignore it, so you can watch it later if you're interested. We also have this ansys stats command, which can be used to generate statistics from the report file. So you can write your own scripts, for example, Python, to create your own statistics. So take the SX, or you can also take the existing scripts, which are available as templates. And another command which might be of interest for you is the Ansys export command, which enables you to put the data into formats like SQLite, CSV, JSON, HDF5, etc., which can be pretty handy if you want to do some data mining stuff and take a look at the data yourself. But you have to be aware that this can take quite a lot of disk space. So the Nsight Systems report itself is packed, and if you're kind of exporting it to such a format and you already have 1 or 2 gigabytes of a report file and then kind of export it, this can create quite a couple of data. So just be aware of it. So here are a couple of switches that I think are important to know about. So let's quickly go over them. And as I said, you can always type ansys profile -- help to find out more about all the available switches. So one of the most important ones is the tracing switch, which is -T or --trace with the default options CUDA, NVTX, OS runtime tracing, and OpenGL. But there are a whole lot of other features which you can kind of select. All right. Something which is important if you're kind of redoing experiments multiple times and you want to just override a report and then kind of visualize it again, you can force override. So the default here is false. If you want to override, set it to true. I'm using this pretty often. If you want to directly get summary statistics in kind of a flat profile on the console after your profiling run, use --stats and set it to true. Then you get some similar output that you might know already from NVProf. And also pretty important is to give your profile report a name, just to make sure that you can find it later easily. And it's also important for the MPI programs. But a few more details here in one of the following slides. For CPU side tracing, we support CPU sampling. CPU side activities, we support CPU sampling. However, sampling can increase the overhead of profiling quite a lot, especially in terms of measurement time and report size, of course. It is enabled by default, so if you do not need CPU samples, you should switch it off to kind of reduce the report file size and maybe reduce the overhead in terms of measurement time. And also, if you want to have proper samples, you also need to set an appropriate paranoid level, so make sure to have the right paranoid level set. There's also a switch to have CUDA memory usage, and there are switches to track CPU, GPU page faults in case you are using unified memory. So there's a whole bunch of other features, which I'm just not showing here, which might be interest for you, especially if you're going to multi-node analysis, are the ways how you can kind of prefix the ansys profile command. So there are basically 2 ways. If you're a single node, you can prefix ansys profile before the process launcher, so something like before MPI run, and then you get 1 report file. You cannot do that if you're going multi-node. Then you have to prefix the ansys profile command before the application executable. So in between MPI run or srun maybe, and your executable. And then you get 1 report file per rank. So in the latter case, you have to make sure that the name of your report file, give the report file a proper name. So you should use this placeholder mechanism with this %Q to add, for example, the MPI rank to the report file name. So here for OpenMPI, but there are also environment variables for MPitch and also for Slurm, which you can use here instead. All right, if you want to profile only a specific rank, then you can kind of use this helper script rezone, which is kind of shown here on the bottom right of the slide. One last hint for the profiling part here. On some clusters, the temp directory is super small. So for example, just 100 megabytes, all stored in main memory, which is, well, pretty often the case in newer HPC systems. And since Nsight Systems is writing the temporary data in /temp, you should know that you can use the temp_dir variable and set it to a specific other location, and then Nsight Systems will write the temporary data there. So just in case you see crazy errors, that might be because you're running out of memory temporary memory where Nsight Systems wanted to write to. And on the bottom here, you see just some output, which is additionally generated after your application output from Nsight Systems. All right, so this is when you enable the stats output, you will get a couple of statistics printed to command line, which should look pretty familiar to you if you already know NVProf. So compared to it, Nsight Systems also provides information on OS runtime APIs, and now you can see where you're spending your time waiting on the CPU, for example. So this even gives a little bit more information than we had before with NVProf. All right, okay. So since it has been proven to be valuable, I also want to give you some information on the NVIDIA Tools extension, so which allows you to better correlate your source code with what you will see in the timeline later on. So let's have a few more information on the NVTX. NVTX is NVIDIA's API for code annotation. It's header only, so you don't need to link any additional libraries. You can just include the header file shown here in the first line of the code snippet. And it allows you to mark a point in the code with this NVTX mark function, or annotate code regions with NVTX push pop ranges or NVTX start end ranges. You can also use it to annotate resources. This is in one of the later slides, I think. So if you're going to use NVTX, you have to make sure that you are also see it in the timeline, and they can do it by adding the NVTX to the tracing options. So it's already in there by default, but if you're kind of manually setting the trace options, make sure NVTX is in there. NVTX itself uses domains to group ranges and markers. So an NVTX domain gets an own row in Nsight Systems, so it is somehow highlighted or well, at least separated from our resources and domains. So otherwise, if you do not specify a domain, the range is put into the default domain. And you can also use this complete domain API and always pass in 0 to specify the default domain. All right, so the functions are all the domain functions, where you can specify a domain start with NVTX domain, and then you have similar things as the other APIs like range push, range pop. Okay. And at NVIDIA, we use a different domain for each library. So NVSHMEM, Nickel, and QBLAST, for example, they all have their individual domain. And for additional subgrouping, you can use the NVTX categories. I'm not going into detail here because this is not used very often yet. You see that you also need to use an NVTX attribute now. So since the NVTX domain range push X function, so for extended, and the NVTX domain range start X functions, they take the domain handle as the first parameter and such an event attribute as the second parameter. Here in this code snippet, you see a normal ASCII string, and you can pass a couple of more properties to the event attribute like color, category, and payload. And especially in terms of payload, there will be an extension which will hopefully be public already in a couple of weeks maybe. So NVTX also provides annotation functions to name the resources. One is on the bottom here. So and this one kind of names an OS thread. So pretty simple one. All right, so in terms of reducing the overhead of your annotations, you should use registered strings. So what does it do? This allows you to register a string, for example, at initialization time, so where it doesn't hurt, and then use the NVTX string handle instead of passing an ASCII string into kind of each of these NVTX range push or start calls. And this can reduce the overhead quite a lot. So to use the registered string, you also need to use an NVTX event attribute and just change the message type here to NVTX message type registered. So this is also highlighted here in green color in this slide. If you want to know more about NVTX, you can just go to the GitHub page, read the documentation, and well, there's a whole bunch of other APIs and details where you can read. I'm now in the pretty lucky position to tell you that the NVIDIA HPC SDK Fortran compiler provides NVTX Fortran bindings. So this is a quite recent addition, and it does not cover everything yet, but it is straightforward to use. So you just need to link the libnbhpc-rep nbtx library. So this is how this library is called. And in your Fortran code, you can just use this like use nbtx to use the nbtx model, and then call nbtx start range or end range. Well, at least for this super simple case, we are just passing an ASCII string directly in the default domain. So since the HPC SDK is for free, nothing hinders you to get the NVIDIA Fortran compilers. But if you still want to use a different compiler, then you can use very simple NVTX Fortran bindings in the link I've on the bottom here of the slide. So then you have to build the Fortran module yourself, but the API then is pretty similar, but it supports only, as far as I know, well, very simple things like NVTX start range and NVTX end range. So no registering of strings and nothing more complex, which is available in the NVTX API otherwise. One last thing about NVTX, there are Python bindings, and you can either use decorators or the context manager. What you have to do is you have to install the NVTX Python module, or if you are using PyTorch with CUDA support, then you can use the NVTX annotations, which is shown on the bottom here, which looks super similar to the C API. So these two ways you have, and in the middle of this slide here, I'm also linking some blogs where you can kind of read more on the NVTX annotations with Python. So for all major languages, whether you have NVTX annotations. All right, so that's it for the introduction slides. Let's now take a look at a short demo report. So I've chosen the TLeaf mini app, which is a Fortran app using MPI and CUDA, and you can download it from the link on the bottom here. I didn't do a lot with the code itself, so I added a single NVTX range in the update halo.f90 file. So I basically added 3 lines there: use NVTX, call NVTX range, start range with update halo, and call NVTX end range. And that's basically it for the preparation step. And then I build it and run it on the Jewels booster system. And yeah, here are the commands to run it. So without profiling, obviously you can just use srun, MPI run, and then start the TLeaf binary. If you want to add profiling with Nsight Systems, then you have to kind of prefix our nsys profile command before the application binary. And I used those options here. Well, I'm not sure. I even probably did not use the UCX options. We will see that later in the demo. And then I'm specifying the output file, how it should look like. I'm taking the slurm proc ID here because I'm running with srun. At least I did that for the demo. And here I also specified I wanted to see the stats output. If you want to add sampling, for example, also for the GPU, then you have to add a couple of additional parameters. You can all take a look into nsys profile --help to figure out and well, read a description on what all those flags, all those switches mean and how they can be used. Okay, so let's take a look at the demo. Coming over here. So I hope that you can see my Nsight Systems windows. So when you first open your Nsight Systems, your first Nsight Systems report, and you did not click do not show anymore here, you will get this, well, grayish area. And on the top right, you will see if you have a diagnostic error, that you will get this checkbox here. Right, let's close it. And if it kind of shows us to look at this error, then let's do it. So this one here basically tells us that some events were lost and what we might, maybe we should kind of decrease the sampling rate. So this is what this error here says. So it's not super important, but we should think about decreasing the sampling rate. Another thing, what is shown on the top here with a warning, you see that I had another or didn't have a low enough paranoid level. So I couldn't do complete back traces and couldn't take CPU kernel IP samples here. So yeah, all right. So let's move back to the timeline view. Usually start up with this view over here. The timeline is the main view, and on the left here we have the row labels, which, when everything is collapsed, represent a resource, each of these rows. So when we expand the rows, then we will see individual domains of these resources. What you can also do is you can also open a new report. So for example, go over here, take a new report. So this one I've just created before, and I opened it with Nsys UI, and then a report file name, but you can also create a report file directly from the GUI. What you can do here is you can kind of select the target, maybe this one, and then you have to kind of enter your password. I'm doing this right now. And then it will kind of set up the connection to a remote system. In that case here, I'm in my Windows guest VM, and I'm kind of only connecting to my host system, which has a GPU installed. And then you can start and fill out, well, what you want to execute, where you want to execute, and kind of check what kind of features you want to see. So I've prepared that project already. So let me go to this other project where I already have the commands in here. Makes it easier and faster for me. So what I did is I specified MPI run here with the complete path, taking 2 processes, and then the executable. On the right here, the working directory is usually figured out by Nsight Systems itself. What I also did, I marked these checkboxes to start profiling after 1 second, limit profiling for only 5 seconds. And then you can kind of go over through all the features which are available. And then you can, for example, say, well, I want to see NVTX information of my program. I want to have a look at what's available as communication libraries. So we have here MPI, OpenSHMEM, and UCX. So I want to see MPI and UCX. And a little bit, of course, also something what's happening on the GPU. So I've been checking CUDA, also OS runtime libraries and CPU context switches. So if you make if you do something wrong, like maybe you didn't specify the binary correctly, let's do this first. Then you will get something like this. So an error over here. Let's change it back here. Let's start it again. Then profiling starts. You can, if you want, you can stop it earlier. So it shouldn't be that long because I restricted it to 5 seconds. And then all the data is copied from your remote system to your local system, and then you will see the report similar to the one that I've shown initially. All right, so that's it on how to trigger an application from the GUI. Let's switch back to report that I took on Jubil's Booster. So I'm taking this report here because it also allows me to show you that we can kind of provide counters for the network interface cards. So that's why we are looking also at this point here. Maybe one more thing before stepping into the timeline. There's also an analysis summary which shows you kind of all the details on how your environment was set up when you did the profiling run. So you can scroll down here and you see what kind of hardware was in the system. You can see the profiling command again and things. So, but since there's not much time left, let's switch back to the timeline. And you see that there's a window which is empty on the bottom here, which is called the events view. To give it some data, you can just right click on one of the labels and show an events view. And then you can kind of see all the events in this row, yeah, one after another, and you can kind of search through it if you want. So you can also search by description, for example, and then let's say we are looking for an MPI function which has a destination maybe 3. I know that this should be in here, and then we should figure out all MPI calls which with the destination 3. And then what you can do is you can kind of click on it, and then it gets highlighted in the timeline. So maybe let's go a little bit in the middle here and see what so you can zoom in by kind of click and move your mouse and then double click, or by using your middle mouse wheel. And so we're moving into one of these iterations here. So here is the selection of the specific function, of the MPI receive function. You can click on another place, and then you can hover over it, and then you can see with a tooltip what happens down here, what is the communication partners, how many bytes have been received, and what looks the communicator like. All right, this is what you can do if you're using the advanced view. Let's kind of give us a little bit more vertical space and move this down here and reset the zoom maybe a little bit again. Start on the top here. You see all the NICs. So mainly there are two NICs network interface cards are doing some communication. Let's hover a little bit over it, and what you see is like bytes sent and bytes received. We tuned this feature a bit, so we'll now see megabytes and gigabytes per second, not this strange unit as you can see it here. So in the new version that looks all better. And there's also an indicator which tells you that the switch behind this NICs is congested. So we improved this feature. If you're moving down then a little bit to the CPUs, you see that we have 96 CPUs in this trace. We opened it, we had only 2 allocated, and they are barely using they are barely sharing a time where they are both fully utilized. So that looks good for an initial view. Can collapse this again. Then we move into this strange row here, so which has a lot of bars in there. So maybe let's zoom in a little bit to see a little bit more. So over here, so what does it tell us? So the upper bar here says that gives us the average CPU utilization. The bar below with the color coding tells us on which CPU is active, and the next one is telling us what the thread state is. So in this case here it is running, and then there's also a little bar below here with small dots. These are the sampling points, and if you kind of move over those sampling points and you're lucky, you get a complete call stack here. But as the warning said, this didn't work well, so we should kind of decrease the paranoid levels over here. All right, so the other rows here then are other domains like the MPI domain or the NVTX domain, which I kind of added manually in there. So if you're, for example, zooming into one of these update halo functions, which are instrumented, and then click on them, then we also get highlighted what is actually related to this range, which I marked here. So we have some MPI calls which are related. We have some CUDA API calls, and we also have a couple of kernels which are kind of finally executed due to this highlighting here, or basically inside of this update halo range. You can click somewhere else to kind of see again the normal coloring. Here are the CUDA memory transfers, here are GPU kernels, and maybe for last thing, let's have a look on the kernels. So if you want to figure out which kernels dominate, you can kind of expand the kernels row, and then you see that there are 2 kernels over here which dominate the runtime. You can kind of take a look at the names here, and then you can also take a look at the GPU metrics on the bottom, which tell you maybe what could be the bottleneck over here. So the occupancy looks pretty good, but if you kind of, for example, look at the DRAM bandwidth and hover over it, you get the values, and you see that this might be something which tends to, well, let me say that these kernels could be, for example, memory bound, but this is something which can be much better answered by Nsight Compute. And I think this is a good point where we should hand over to Felix for Nsight Compute part. All right.
Excellent. Thank you very much, Robert. I very much enjoyed the live demonstration, and we're going to have another one of those to come, I believe. So now that we've spent some time with the Nsight Systems tool, this will be complemented nicely with today's final talk on Nsight Compute. This will be given by Felix Schmidt, a senior software engineer at NVIDIA's developer tools team. There, he develops a range of performance analysis and correctness checking tools, of which Nsight Compute is just one. Prior to joining NVIDIA, he was working as a research associate investigating novel performance analysis tools and techniques, and he also holds a master's degree in computer science from Dresden University of Technology. So, last but not least, I'd like to hand over to Felix for the third and final talk today.
Yeah, perfect. Thanks a lot to both of you. Yeah, I hope you can properly see the slides and everything. So as Robert mentioned, right, there are the three tools: Nsight Systems, Compute, and Graphics. And once you have identified that there is some problem with the CUDA kernels in your application, then you might want to switch to Nsight Compute to optimize these further, analyze them in detail, and just better understand what the hardware is doing under the hood. A couple of introductory slides before I switch to my demo as well. Nsight Compute is an interactive CUDA kernel profiler. It has targeted metric sections for the various performance aspects of your GPU. So there are kind of sections that group high-level metrics, sections that group memory metrics, compute workload, occupancy, and so forth. And that's because there are just a lot of metrics that the tool can collect that can give you insight into the GPU. But if you're not familiar with them, it might be hard for you to choose which ones to select for profiling and what they mean exactly. So that's we kind of curate them for you and group them into these logical domains. It's also a very customizable tool. So most of the things that you can collect or how to show once they are collected can be customized. It has a user interface that we're seeing here, as well as a command line. And you can collect and inspect the data in both ways. There is a Python-based API for both the guided analysis or expert system within the tool, as well as for post-processing, similar to Nsight Systems. Once you have your report and you want to integrate it into your own analysis workflows, maybe because it's for many thousands of kernels, you can do this in various ways, including this Python API. And it has support for remote profiling across machines and platforms. The three kind of main profiling activities are the interactive one that I'll demonstrate, the non-interactive one where I'll be showing a pre-collected report today, as well as the command line, which I'll only speak to in this talk. Once you have a report collected and you would open it in the UI, there are various what we call pages to the report. In this case, for example, the summary or the details page, which kind of just show you different aspects of the report. The summary page shows you kind of which results were collected, like which kernels, for example, were profiled. And then for each individual of these kernels, you could switch to the details page and see these metric sections that I spoke of earlier to see what is the overall GPU throughput for this kernel, what is the usage of my compute pipelines, and so forth. And there are more pages, especially to inspect the source code, see metrics correlated with the source code, and so forth. A couple more details to this details page itself. So on the top, you will see this kind of what we call the summary header, where you can select a page, where you can select the current results to be inspected, and do some operations that I'll talk to later. And then in these sections, they are normally grouped into the header, which has a couple of metrics that are considered to be the most important ones that you should always see. And then these rule outputs, the guided analysis or expert analysis, that is probably the most valuable part of it, that was written either by the experts at NVIDIA or by you yourself, if you want to understand what do these metric values mean to me? Is it good or bad? And what could I do to improve them if there are any problems detected? And then you can expand these sections to get even more insights, charts, histograms, diagrams, and more. One of these charts that you can get is the memory workload analysis. There are both charts and tables to it. And it's a very neat view to see kind of the different units in your hardware, or at least a selection of the units, and the data transfers or throughputs that were measured between them. How many instructions on your SM accessed global memory, and how many sectors were loaded from DRAM into your L1 cache as a result of that, things like it. And it gives you kind of a heat map to understand, is this link well utilized or overutilized or not utilized at all? One of the coolest features, I think, is that you can compare pretty much everything directly within the tool. So you can compare results from the same report or even across reports, but with what we call baselines. So you can select one or more results as baselines, and then the current result that you're looking at will be compared to these baselines. And you can see, once you made an improvement to your kernel, hopefully an improvement, what is the difference? Did it get faster, slower? Is more memory transferred or less? Things like that. And I spoke to source, so there are a lot of metrics that are correlated with individual source instructions or lines of source. And the source page basically shows you the low-level assembly, or called the SAS, of your CUDA kernels. And if you have that information, then it also shows you the correlated high level. For example, CUDA-C, CUDA Fortran, or OpenACC. And you can see a lot of metrics that are correlated with each lines or each instruction to better help you understand where was my GPU stalled, not only in time, but also in terms of in which individual source line or loop was the problem, and where do I have to optimize. So this is really helpful to kind of find the hotspots within your code. There's also an occupancy calculator. Users who are familiar with the CUDA Toolkit's Excel spreadsheet, that's basically just a way to do the same thing directly within the UI. And I mentioned the command line. I won't be demonstrating it today, so I just want to give two examples for your reference. The command line is called NCU. And in the first example, we are collecting a set of sections, so even kind of a super group, because often you want to collect multiple sections at once to get a better overview. We're collecting the full set here. We're filtering the kernels that should be profiled using a regular expression. And we only want 10 kernels, force override any existing file, writing the report into a file called tleave, actually having a placeholder to auto increment kind of the numbering of the reports, and then the application that is profiled. In the second example, which is kind of the inverse, we are taking a pre-existing report using the --import or -i operator, importing that, and then printing the first two kernels that we find on the raw page, which is kind of a way to show like all the data that is within the report in more like a table view. Format that as CSV so that it can be more easily post-processed using further scripts, and limit the metrics that we want to inspect to the two that are listed here in this example. So this is just to give you two ways to start to understand how to use the command line. All right, perfect. With that, I'll also be switching to my example now. I also use this tleave CUDA. I'll be showing part of it kind of live collection and part of it using a pre-collected report, which was done using on a different system that I'm not on right now with a GA100. Right now, I will be connecting to a system with a Turing card. And similar to Robert, I added some NVTX instrumentation just to highlight how that feature can be utilized with Nsight Compute as well. I added 3 ranges using the push-pop operators in the code, a larger one called update and calc, And then for the individual kernels, there's an update kernel and the core kernel that we'll be looking at. There is another range on the stack called update and called cork. All right, perfect. So yeah, basically you should have used Nsight Systems to figure out which do I want to improve kernels? Do I need to improve kernels in my application? And if so, which ones? It would have shown you that you need to analyze the PPCG solve calc and solve update kernels in this particular application, at least when running on an NVIDIA A100 GPU. So let me switch to Nsight Compute. And as the first step, I will be using the interactive profile activity to remotely connect to a different system. And at this point, the application tleaf is launched on the remote system and kind of gets suspended in the first CUDA API call. And we're seeing in this API stream on the left-hand side where we are currently. We're currently in this kupointer get attributes. And what I can do now is I can pretty much step through the CUDA API calls of the application. So using the buttons here on the top or using F10 like in a debugger, I can step between them. And because some of them return error codes in this case, Nsight Compute highlights that for us here. It doesn't mean that the application is actually having an error. It just means that this particular API call returns not success. What I can also do is I can say, okay, run to the next CUDA kernel, because often you might not be interested in inspecting like your function parameters or return codes, but really to see which kernels are launched and then to profile them. And before I actually profile it, we want to remember that it's the update and the core kernels that we're interested in. So I could, for example, put in the names of these kernels into this next trigger edit, and then tell the tool to forward the application until it reaches these kernels. Since I instrumented them with MBTX, I can also use MBTX expressions and say I want the application to forward to the next kernel that is in an MBTX push pop range that ends on update, or that has update on its stack. And then I can use run to next kernel. And sure enough, it will be at the solve updates kernel launch, kind of right before the kernel is actually launched on the GPU. And I can verify switching to the MBTX tab down here that I'm truly within this MBTX context, which has two ranges on its stack, update and cork and update, and also another, not on a push pop stack, but as a start end range. I could also inspect the CPU call stack to see, okay, where is this kernel launch kind of on the CPU side in my application, see what the current status of all the CUDA resources is, or the optics resources for that matter, if the application were to use optics. So for example, it might be interesting to you to see which memory allocations were made at this point. So right now, the application allocated 2.6 gigabytes of GPU memory, and you can see all the various individual CUDA allocations with their properties. Or you could see the number or the CUDA modules that are loaded, the CUDA streams, and so forth. And once you are at the right kernel, you would select what to collect. For example, the full section set, and then select profile kernel. And at this point, you would get a report for this particular kernel launch, and you could switch between its pages. And you also see that this MBTX state at this launch point was actually embedded into the kernel, into the result, into the report, so that later, when you want to filter the report for inspection or analysis, you could even say, okay, for this collected report, show me only the kernels that were in a particular MBTX context, for example. Or we could look at this raw page that I mentioned that will have all the metrics that are currently collected for this particular result. And if I were to collect another result in this report, I would see another column over here. All right. So I don't actually want to inspect the performance of this particular report because it's on Turing. I'm more interested in the performance on my Ampere card. So that's why I pre-collected one report here. And so this report has 10 results collected, actually for both the update and the core kernels. And the summary page gives us kind of a broad overview. How many results are there? What kernels are those? And what is the rough compute and memory throughput? And we can see already that they all run for around 500 microseconds, not too long actually. They have pretty good memory throughput, but pretty poor compute or SM throughput. And as I double click one, it takes me to the details page where we'll see these sections, these logical domains that we can use to analyze the data. When you start out with Nsight Compute, you might not really be too familiar with all the terms or anything. And the way it looks when you open the tool the first time is actually there are a lot more descriptions in here to really tell you what is going on. As you become more familiar with everything, they might be a little disturbing to see them every time, to take up screen space real estate, so you can just remove them. And as I mentioned, you can expand these sections to get more insight into each individual one. Another interesting thing is that these sections are grouped or ordered from roughly high level to low level. So often it makes sense to start on the top, kind of read it like a page, and then either go down the sections one by one to get a better understanding, or if there are any, follow these warnings and rules that the tool presents to you. So what I can see from the top section here, as I said, my application has, or this kernel has very low compute throughput, very high memory throughput or utilization. So the tool suggests to you to improve something about the memory workloads actually, because the memory units seem to be the ones that limit the performance of the kernel at this point. So I could either manually go there or manually go to the next section, excuse me, or I could select these section links that just take me from one section to another and kind of guide me through the report. And as you go, or as it takes you to the memory workload analysis section, what we'll see is, yes, the bandwidth is really highly utilized, 80%. And we can use the chart to find out where that happens. So we can see that most of the transfers seem to be between device memory or DRAM and the L2 cache. There are around 380 megabytes read from device memory, and that makes up around 760 gigabytes per second, which is roughly, at least for this read-write part of device memory, of the device memory unit, 80% of the peak utilization. And then what you would do next is you would read these warnings. You would read the guided analysis to understand why are you at these values, and what could be done to improve them. I don't want to go through the results into too much of a detail, just showing you that conceptually you could even expand those further a lot of times to see more of the reasoning why the rule was triggered. Why did the rule show you this warning? In this case, because the sectors per L2 request value was under a certain threshold. And as you would read the warning itself, it would say, okay, there are 4 consecutive 32-byte sectors per L2 request. However, this kernel only accesses an average out of 3 out of the possible 4 per cache line. And that's kind of like suboptimal. And then it will tell you, okay, you might want to know where that happens. And for that, you can go to the source counter section, which, among other things, allows you to see where you have these excessive L2 excesses, for example, or another interesting thing, where warps are stored. So warps are a unit, like a execution unit or a logical unit within your kernel. It's like a grouping of your threads in your CUDA kernel, 32 threads. And the schedulers on your hardware might be able to issue an instruction to a warp or not. And if they can't, that's what we call a stall. And there is a way to sample these stalls over the runtime of your kernel to see where the hotspots, where is your application stalled most of the time in terms of like where you source. So we could either proceed to understand where are the source accesses, where are the memory loads suboptimal, where does we don't utilize the DRAM to L2 link fully, or where's our application stored. We can also see, I mean, there are way more sections on top that I just skipped for the sake of time to give you all this detail, but we can already see in the summary table, or this summary table, the individual types of stalls that have occurred. And in this case, it's these long scoreboard stalls that make up almost 100% of the stalls at the source location. And if you were to read the documentation on it or use some of the hints that are further up in the report, it will tell you that long scoreboard stalls are associated with loading from global memory. So these two problems seem to be closely correlated, which makes sense. So let's click on one, and it takes you to the source page where it will highlight the instruction at which these stalls were measured. In this case, this double multiply instruction, FP64 multiply, and we have the summary of stalls here, which are these 26,000. But of course, there are way more metrics that you could use to understand what is happening at this source location or at source locations close by. And as this instruction or as you select this line or the tool does it for you, if you have your high-level source on the left-hand side, what's happening is that it correlates that instruction back to the high-level source line where this happened, this line 239 here. So that because normally you don't write assembly, right? You write like CUDA-C or Fortran, so that you can understand where was that in the code that I've written. But because the compiler generates more than one instruction for this particular source line, it then highlights again on the right-hand side all the other assembly instructions that are also correlated with this line on the left-hand side. So as I click this one, I can nicely understand, okay, this one kind of belongs in this group of instructions, which all belong to this line on the left-hand side. And you will find that the metrics for the individual instructions on the right-hand side, for example, for the warp stall sampling, are then aggregated to the metrics on the left-hand side. Another nice feature that you can do is you can collapse and expand both on the left and then on the right-hand side, these things. In this case, it's not too useful because I only have a single function. But what you can see is it aggregates all the data for this function. And if you had more functions, like 10 of them, then you would see nicely, okay, which of the functions have most of the stalls or most of the instructions executed. So this way you can get a very good overview over where in your code things are high, where things are low. All right, with that, let me quickly switch back to my slides. I'll be skipping a few slides now, which are basically just what I explained to you. I put it into the slides for later reference as well. And I want to talk about a few more aspects of the tool besides the data collection, besides the performance analysis necessarily. So as I mentioned already, there's also a command line, which you will predominantly use if you are on like an HPC system with a batch environment. And by default, everything from the command line that the command line collects is reported, is printed to standard out. And that might not be what you want. You might want to put it into a report using the -export flag so that you can later load this report in the UI, or simply inspect it in more fine-grained detail at a later time. Similar to Nsight Systems, you can use placeholders and environment variables. So if you invoke multiple NCU processes at the same time as part of an MPI program, for example, you could write a report for each rank, let's say. I already showed you the sets or the full set to be collected in the UI. And there are a couple of sets that we define. Sets are collections of sections themselves. And the sections are kind of these logical groupings that I've shown in the UI on the details page. And you can combine them as you want, right? You can say, I want the full, or I want the source set, or let's say the default set combined with the source counter section, and then this additional SM-int executed pipe tensor metric, let's say. So you can really pick and choose on the command line as you want. If you want to go beyond the curated sections on collecting metrics, that's totally possible. You can query which metrics are available either for the current system or for any chip that the tool supports, even if you don't have the chip locally, by using the command line /query metrics option. And then you will get a list of kind of base metric names that you then often have to, or most of the time have to suffix with their kind of submetric suffix. And the suffixes, they differ a little bit between the types of metrics. That's why there's an additional query metrics mode suffix that you could give the base name, and it will tell you which suffixes are valid for this particular base metric name. About the source analysis that we've already seen. So the SAS assembly, it's always available in the report because it's embedded as part of the Kubin. And the CUDA-C, CUDA Fortran, or PTX availability depends on your compilation flags. So if you want, let's say you're using CUDA-C, and if you want the compiler to embed this correlation information that we used to correlate the left-hand and right-hand sides, you need to tell it about it. For NVCC, that's the -line info flag, for example. But if you're using like a different compiler, like a PGI compiler or something, that flag may differ, and you need to check with the compiler vendor basically what it is. The source itself is not embedded into the report though, mostly for security reasons, right? You might not want to accidentally share a report with somebody else and reveal all your source code, or because it's not really necessary to have it every time. You can choose to import it though, in which case you don't need to kind of preserve it locally for later resolving it in the UI, but it will really be baked into the report, and it's just there, always available. Which can also be useful if you want to understand or see partial optimizations, right, on the same source code. Then it can be very tricky if it's not embedded in the report, because the local copy on disk will change, and as you make new profiles, your older profiles will refer to source that's not available anymore. One last comment about replay modes. So the cool thing about Nsight Compute is that it does pretty much everything for you already. You don't have to instrument your application. You don't have to worry about buffer management, about save and restore. So the trick is that, or the problem is that the hardware cannot necessarily collect all the information that you wanted to collect in a single pass. There are only a limited number of performance monitors, and if you want more metrics than that from your kernel, which is most of the time the case actually, or if some metrics might interfere with others, then the kernel needs to be replayed, needs to be run multiple times in order to collect all the information that you want for it. And obviously, if you don't make changes to your application, rerunning the same kernel multiple times is not trivial. It requires that all the context of the kernel, like the memory you can access, is saved, and after each run is restored so that the kernel is deterministically and reliably always run on the same data. So that's what we call kernel replay. It's kind of the default mode that it works. And each kernel will individually be replayed as many times as necessary. There's a second mode called application replay, which does not require to save and restore to memory, but to rerun the whole application n times for n passes. And then the save and restore of the memory will be implicit, basically. So that has the benefit that, let's say, if your kernel accesses like 80 gigabytes of your GPU, we don't need to transfer these 80 gigabytes to some backup location. The application just can behave as normal, but needs to be run multiple times. So there are trade-offs, there are pros and cons to both sides, and you need to choose which one works best. If there is a lot of save and restore overhead, kernel replay will tell you about it and will suggest to switch to application replay. As a last comment on that, the problem with kernel and application replay is that it serializes your kernels. It will run each kernel one at a time to collect the very deterministic information about that kernel in isolation. But sometimes you might need to run kernels in parallel and measure them at the same time. Or you want to run them in parallel because a kernel by itself, won't fill the entire GPU, NA100, for example. And for that, we have a very recently new mode called range replay, where you have to define a range in your application, for example, using NVTX, which you'll hopefully have in there anyways. And then this range, including the kernels and API calls, will be replayed multiple times. And you will get profile results for that entire range, with all kernels within this range being run in parallel, which allows the kernels to communicate with each other. So just be aware of the different modes for your different needs, basically. Yeah, with that, let me quickly wrap up so that we have some time for Q&A. Nsight Compute enables detailed CUDA kernel analysis. Please stick to the rules. They give you really good guidance on optimization opportunities and help you understand the metrics. Limit metrics to what is required when overhead is a concern. And if you don't understand the term or one of the hardware units or how you think they'll work, refer to our profiling guide or the CUDA documentation, for example. You can analyze results in the UI, post-process with Python report interface or CSV. And for further reading, for your reference, those are like kind of the documentation links or links to further information. All right, perfect. And with that, I think we can switch to the Q&A part.
Indeed, that's wonderful. Thank you very much, Felix. And another thank you to both Paul and Robert as well. Just a quick reminder for the audience, if you have any questions, then now's the time to go ahead and write them in the questions tab so that I can read them out for you. And so now, just whilst we wait for the questions to start coming in, I've actually got a couple myself. So first of all, do you have any examples that you're able to give of the Nsight toolkit being deployed for enterprise applications? That's kind of directed at anyone there.
What do you mean by deployed? Can you specify that a little further?
Yeah, sure. So instances where the Nsight toolkit has been used to optimize applications in the enterprise setting, or maybe in industry, for example.
Yeah, certainly. I mean, it is, I'd say it's used right internally within NVIDIA as well as by our external customers, research institutes, for all these, on the one hand side, for all these applications that Paul pointed out earlier in HPC space, but it's also used by, like enterprises, let's say the Adobes of this world, right? Where you have an application that uses CUDA for optimizing a certain part of processing, say in Photoshop, or for running an optics application, right? It can profile your optics workloads. So you can, it was used for optimizing the cycles renderer in Blender, for example, which is based on optics. So really anything that uses CUDA directly under the hood, or to some degree uses CUDA accelerated libraries, these tools are valuable. And with Nsight Systems, even more so, because there's both the compute as well as the graphics aspect to Nsight Systems. So it's also like the graphics tracing part of Nsight Systems. It's also used by all the like game developer studios, for example, that need to optimize their applications for games or game engines. Does that answer the question?
Yes, it certainly does. Thank you. So before I ask any more of my questions, I've seen that there's one that's come in on the questions tab here. So this one's actually directed at Paul. So CFD codes are generally memory rather than compute bound. So would features like multi-instance GPUs help alleviate this? And are there any developments in the pipeline that may help bandwidth limited applications?
Okay, right. So the multi-instance GPU is actually more aimed at making better use of the GPU. So if you have the example I gave earlier was with if you have several researchers sharing a resource, you can actually support them each running like a session on that GPU, up to 7 different people on the same GPU. Similarly, you could run several applications on there. I'm thinking of situations, for example, like the world of deep learning, where you're doing inferencing. The actual inferencing itself may not require the whole GPU, but you might have 7 different deep learning models running at the same time, all doing their own inferencing. You can have those on these separate multi-instance GPU instances. So in terms of the memory bandwidth on the GPU, GPUs actually have a very high memory bandwidth compared to CPUs, pretty much an order of magnitude higher. The challenges with the GPU though are, in terms of the programming model, you actually want, you get a lot of speed up from having data sets where the data is aligned with the actual compute cores they're running on, which is called coalesced memory access. And basically, it means we can issue instructions in such a way that we can operate on lines of data rather than just individual data elements. And there have been challenges in the past with CFD codes not mapping well to that model. However, in the last few years or so, you've seen more and more CFD codes come to the GPU. We have things like ANSYS Fluent, I know it runs on the GPUs now. OpenFOAM, there's been work going on for years on that, and some good progress is being made there. NASA have a code called Fun3D, which again is a CFD code, and that again can take great advantage of GPUs. So there are CFD codes on GPUs. They're just taking a while to get there. And I also think one of the challenges with CFD codes is quite often they have quite high demands on memory in terms of capacity rather than bandwidth. If you think of the large models that you want to simulate, but of course the modern GPUs, whilst the memory is not as large as the CPU memory, it's very much faster. But you know, we have 80 gigabyte cards now, so that can really help with things as well.
Sure, thank you for that. So I haven't got any more questions in yet, so I'll ask a few more of my own. This is directed more.
Sorry. Yeah, sorry. Just before you do that, I just wanted to expand on one thing that Paul said.
Oh, sure,
so he mentioned these coalesced access problems for the CFD codes, right? And he also mentioned that the bandwidth is most of the time not the problem, but kind of the latency is having compute and memory access as well aligned. And this is precisely what we've seen in the Nsight Compute example. We had the tool point out that there were uncoalesced accesses where we weren't loading the cache lines as efficiently as we could, and that these loads were also stalled. That's what the long scoreboard warp stalls that we've seen. So the GPU was stalled from making forward access because we had to wait on the memory. It wasn't available at the time where we needed it. So that's kind of how the tool can help you alleviate or at least identify right where the problems are.
I see, thank you. So whilst you were answering that, just had another question come in referencing the first talk. So I assume this is directed at you again, Paul. It was described that compilers can interpret Fortran or C++ language and run the code on the GPU. So the question is all the code running on the GPU or only some bits, i.e. matmul in the example?
Okay, so in that particular example, I guess the question is related to the fact that there was a loop outside the matmul. So the way that would work is the managed memory would handle the data movement. But the way, and so, you don't explicitly move the data. And it'll just be the matmul kernel which runs on the GPU. Now, what you might think there, as soon as that matmul's finished, the data would migrate back, and then you go to the start of the loop for the next iteration, then you're moving data again. But that's not the way the managed memory works. The managed memory just works when you try and access data on whichever piece of hardware you're on. So as long as you don't touch the particular data set being used in the matmul calculation back on the CPU, it will just remain on the GPU and will do so until you try and access it on the CPU. So in that sense, for that particular loop I showed in the example, the data would just remain on the GPU until you try to reference it or access it again on the CPU. So that's the part of the code which runs on the GPU, and what we need to worry about there is the data movement, but it kind of does the sensible thing. It doesn't move it back until it's actually you attempt to access it back on the CPU in your code. Does that make sense or answer the question?
Understood, yes. There was actually a follow-up question there, but you kind of answered it at the same time to do with how the compiler can avoid unnecessary data interchanges between the CPU and the GPU, but you kind of touched upon that in your answer of the first part. So I've got a couple questions for Robert and Felix. So first of all, back on Nsight Systems and Compute, how does one prepare their application for analysis by the Nsight Systems and Compute profiling tools? Is there some assumed level of correctness in the input program, kind of a priori?
Okay, so let me start here. I think I already said a few words about it in one of the initial slides of my talk. So that's a pretty cool thing with these tools, is that you do not need to prepare it in a way that you do not need to do any instrumentation. So NBTX you can put in there, but it's not at all necessary, and you can just prefix our tools, and then you will get a whole bunch of information for both CPU and GPU side. In terms of correctness, I mean, we don't really care about if the program is correct. And Nsight Systems, at least, is also tolerant to some extent if the application, well, does not correctly shut down. So it will be tolerant, at least in some cases, and will still generate a report file. But also the general idea of a performance analysis tool is that you have a correct application which runs without any crashes, and then you're going to analyze it. So the idea is not to do any debugging with Nsight Systems and Nsight Compute as far as I would, well, see it from my perspective. But well, at least there is some tolerance in terms of programs that do not run correctly.
Yeah, no, that is certainly true. I think the key part here, right, is that your application should ideally be correct and stable to a degree before profiling it. Otherwise, I mean, why make it fast if it's not correct? If you have problems making it correct, or if you need assistance in that space, then we do have tools to assist you with that. There are debuggers and correctness checkers. On the Linux side, the debugger we have is CUDA-GDB, and which is basically what you would expect, a GDB plugin or GDB style tool that can also debug on the kernel on the GPU, and it is also integrated into Visual Code, which has become a very popular IDE for developers on Linux systems. And there's a second tool called Compute Sanitizer, which you can think of as the Valgrind for the GPU. So it can check for all kinds of memory access issues, out of bounds accesses, unaligned, misaligned accesses, using uninitialized memory, race conditions on shared memory, things like that. So yeah, if there are problems or if you need assistance making the application correct, or if you see unexpected behavior, I would say, then definitely use these tools.
Right, I see. So I guess a follow-up to that previous question. So so for the more advanced users out there, right, who might require some highly specialized functionality, does NVIDIA provide any libraries that can access the fundamental tools and techniques being used here, but for third-party developers or researchers who might need that added flexibility?
Yeah, most definitely. As I said, right, the cool thing about Nsight Systems or Compute is that they give you a lot of support. They do a lot of kind of hand-holding, but naturally that comes with some limits, right? You might have a very specialized use case that is simply not covered, either because we didn't think about it, right? It just happens, or because it is so special that it just doesn't make sense for us to support it in a more general audience tool. But for that, there are libraries on both the correctness and the performance analysis side that, to a large degree, allow you to do the same thing that the tools do. So on the correctness side, there's the Sanitizer API, which is basically like a public API for Compute Sanitizer. And on the performance analysis side, there's CAPTI, or the CUDA Performance Tools interface, which has APIs for both tracing as well as performance metric collection. So you can technically build an Nsight Compute style or Nsight System style tool using these APIs, and some do. There are a lot of HPC customers, like a lot of HPC tools, Scorpy, HPC Toolkit, what else, I guess, and more. Sorry for the ones I forgot right now, that use these APIs, at least for accessing like GPU counters or CUDA activities.
Sure. Thank you for that. So I haven't had any more questions come in, so I'm going to ask another of my own. So something that I feel is kind of compulsory to ask, right, when talking about high performance computing, and you mentioned this, Paul, as well, is the drive towards the exascale. So as far as I'm aware, the Fugaku machine in Japan is the only that can really make any claim of achieving this, even if only in one isolated benchmark. But this device is entirely CPU based, right? So it was indicated in your talk, Paul, how computing performance will need to be driven forward by GPU accelerators. So what is to come in the near future in this respect?
Well, I mean, I think it's a combination of things on the path on the road to exascale. And you mentioned that Fugaku achieved an exaflop performance, but many of the GPU systems which exist now, Summit, for example, have hit exa op performance. And by that I mean that by using different precisions, they've actually performed these exa calculations. And I think the algorithmic approach needs to be considered as we move forward. You could build an exaflop machine now, you just need to throw enough money and enough power at it. The technology is there, but in terms of running your code on it, are you going to get efficient performance out of it? And so we need to think algorithmically. And so one of the approaches that people are looking at is using mixed precision. Many algorithms can actually manage to use that, even if it's only a part of their calculation, which can, of course, significantly speed things up. Also, on the software side of things, I see a lot of people interested in the applications of AI in this field. If we think about the way we run simulations, quite often for parts of our code, we used reduced order methods to try and approximate things because the ab initio calculations are too expensive. And if we're already using reduced order methods, perhaps we could use AI methods in there. And so what a lot of people are doing is training AIs using the reduced order methods, using the ab initio calculations as well. And once you've trained that AI, they can perform just as well, if not better, than the reduced order method, which you were using anyway, but can do that at pretty much orders of magnitudes, if not several orders of magnitude more quickly. So again, in terms of algorithms, we need to think about that. On the hardware side of things, it's all about the bottlenecks. I mentioned that the data processing unit has been something which is coming into play to perform operations on the data as it's moving through the system, and also freeing up the CPU to focus on what it's doing more. We're looking at things like improving the interconnect between the CPUs and the GPUs within a node. I think we'll see in the next generation of GPUs, a lot of them will support that in a much more coherent way. Removing the PCIe bus, because that's a bottleneck. There's challenges there. People are looking at things like, what other specialized hardware can we have? So we have the tensor cores at the moment on the GPUs, which are dedicated silicon for doing the matrix multiply operations. Are there any other low-hanging fruits calculations which a lot of codes use? But the challenge there is, of course, as soon as you put this dedicated hardware on for doing a particular calculation, you're taking away some of the silicon from just doing general calculations. So you are creating a more specialized device. But again, that's something that people are considering as well. In terms of what we'll be offering, I'm not sure what's coming up. We're quite secretive both within and outside NVIDIA in terms of the next generation of hardware. There may be some announcements at GPU Technology Conference next week, so keep an eye out for that. But certainly, I don't know what's coming next.
Sure, I appreciate that. Well, kind of related to that, I suppose, is I've got a question on the questions tab here, asking what trends in GPU prices can we expect to see in the next few months? Should I buy a GPU now, or should I wait?
Right, that's interesting. So I think the problem is the world is seeing this challenge of shortage in components, and it's not just the GPUs themselves; it's some of the components that the GPUs use to build the boards that the other manufacturers use to build our boards with, and it's across the, it's not just GPUs; it's across anything which has got silicon in it. And what that's meant is that people are basically charging what they can get for GPUs. That's not our pricing. Our pricing is we put it out at a recommended retail price, and the problem is people are trying to just take advantage of the general shortage of that. We're working very hard with the manufacturers of all the different components which go in our devices to try and make sure that we can improve the supply. The supply has already improved, I believe, but it is a real challenge. It's one shared across the industry. It's not just purely with NVIDIA. We are working hard at it, but we're, at some level, we're at the mercies of what's going on in the world at the moment. But there's I think that's all I can probably say about that. I think I don't know if the team have anything else to add.
Yeah, I mean, not really, right? I mean, that goes well beyond our pay grade.
Yeah,
but,
exactly.
I think one comment I can make with like a wink of an eye, I guess, like the chart, like referring to the chart that you showed earlier, right? Where you saw the P100 to A100 evolution in performance. It's not the case that if you buy a GPU now and then sometime later there will be a new one, you're kind of out of the game, right? Libraries evolve, libraries get better, get optimized, and these libraries run on GPUs that we sell today and GPUs that we will sell tomorrow. So just because you buy something today doesn't mean it's worthless tomorrow. And of course, I mean, there will always be another generation, right? So it's kind of, it's always not a gamble, but a trade-off of having something available right away or just wait longer, for the next generation.
Sure. And so, I mean, when you say supply shortages, is that because of, for example, cryptocurrency mining?
No, not really. I mean, that's part of it, but you know, we've made modifications to the board so that there's a certain dedicated type of board which you can use for crypto if that's what you're doing, but it's actually a relatively small proportion of the boards we sell. The main challenge is literally being a shortage of silicon. When the lockdown happened, a lot of people started buying things like home entertainment systems and things, and so all the different, and a lot of the manufacturers had closure issues because of COVID, and so it's this perfect storm of events, which basically meant there's a worldwide shortage of electronic devices, essentially, and we're at the whims of that as well. We don't own our own fabs, we don't make our own stuff, it's all outsourced, so we're dependent on these other places, and as I say, we're working incredibly hard to try and make sure we can supply. We want people to have our GPUs. It's not like we don't want to sell them. The real challenge is the whole supply chain is being in trouble, mainly because of COVID, and we're not the only vendors who are suffering from that.
Okay, I'm with you. We haven't had any more questions through, so I think I'll ask one more myself, and unless anything last minute comes through, I think we'll wrap up after that question. So kind of on the topic that was touched upon a few questions ago now, but on having your codes in a state of exascale readiness, right? And so a tool that many, I'm sure, attending would be aware of is Vecma, which is a general toolkit for performing validation, verification, and uncertainty quantification in the context of HPC. So how does something GPU specific, such as Nsight, compare in this case? So what are the key differences or similarities?
Yeah, I'm afraid I'm not too familiar with that myself, so I'm not quite sure if I can answer that one.
Sure, that's not a problem. Do you have any thoughts on that, Robert, or a similar situation?
Yeah, I'm in a similar situation, so I'm not really aware of Vecma. But since you're saying it's for validation, verification, and uncertainty quantification, well, does not seem to have much to do with performance analysis at the first glance, to be honest. So if it can give us a few more hints, maybe we can answer that one.
No, don't worry. I'll put that one to bed then in that case. So I haven't had any more questions come through, so I think this will probably be a good point to draw the session to a close. So once again, a huge thank you to Paul, Robert, and Felix for giving us their time today to speak about how NVIDIA is optimizing GPU usage for high-performance computing. Just one final reminder that this e-seminar will be available on the CompBiomed YouTube channel and website, which is accessible via the link shown on screen currently. So finally, thank you to everyone in the audience for attending, and I hope that you all enjoy the rest of your day.